Another topic we did not approach in your prior thermo class is the idea of isentropic efficiency. If you think about what happens with a steam turbines don't operate isentropically, right? Nothing operates isentropically. We think that would be the best. In the case of a turbine, it would be the best. So what do they really do? Well, there's always some irreversibility. There's some friction, there's some unrestrained expansion of gases, and what that really means is that the fluid leaves the turbine with more energy than it should have, and in particular, it has more thermal energy than we would like. It doesn't transform as much of the thermal energy into work as we would like. And if you look at the process on a TS diagram, where the fluid comes in at state 1, where it's at 3 megapascals, and it leaves at state 2 at 50 kilopascals, we'd like for it to drop straight down from state 1 to state 2 along an isentropic line. Unfortunately, that's not what happens. The entropy of the fluid actually increases as it moves through the turbine because it's a non-isentropic turbine. It's a real turbine. And so the actual process path is shown as the dotted line in the TS diagram, so that the entropy actually increases. So you see that we end up at a higher temperature at state 2 than we wish. In other words, we'd like to end up at a lower temperature at state 2s, but because of irreversibilities, and friction is the easiest one to understand, right? I mean, if there's friction in the flow of the gas, if the steam has some viscosity, certainly there's going to be some unintended heating that we don't want to have happen, and so, or at least maintenance of the temperature. And so what we'll do is we'll end up at a higher temperature at the exit than we would like. The steam turbine will not extract as much thermal energy from the gas as we would like. So if we concentrate on just that section and what's happening there, we could, instead of writing a TS diagram, we could draw an entropy diagram, because the enthalpy change is something we're particularly interested in, because it's proportional to the amount of work produced by the turbine. The larger the enthalpy change, the more work the turbine will produce. And you can see that by just drawing an energy balance and analyzing one around the entire turbine. The energy that comes out in the form of work must have come from enthalpy, because that's all that we've got, right? We've got the thermal energy and the flow energy, and getting the flow energy out is not too bad, right? The problem is getting the thermal energy to change into work. So while we would like to have a nice large drop from H1 to H2S, rather what happens is we have the drop from H1 to H2A, where the exiting state 2A is the actual state, and it's the non-isentropic process. It's the actual process. So since the amount of work we get out is proportional to the enthalpy change between those two processes, what we can do is define an isentropic efficiency for turbines and say it's the actual turbine work output over what we ought to get, which is the isentropic turbine work output, which would be the specific work in the actual case over the specific work in the isentropic case. And we can write this approximately in terms of the enthalpy changes between those. Now, this is an approximate equation because really the kinetic and potential energy will contribute some to the work output, but often it's so small it's not even worth considering, and so that's the approximate sign. The tilde there is just a nod to honesty, to say that this is not all there is to it, but it's close enough for our purposes. So if we knew the enthalpy in state 1, and we know the enthalpy in the actual exiting state, and we can find what the enthalpy should be if it was an isentropic behaving machine, then we can calculate a so-called isentropic efficiency. And the larger the isentropic efficiency, the more work we'll get out for the same energy input. And that's a really important thing to know. We can talk about a pump's isentropic efficiency. A pump is not a turbine, obviously. It's a device where you're putting work in order to change fluid power. Pumps don't behave perfectly, just like turbines don't. And so the entropy at the exit of the pump will be higher than it should. Pumps are not isentropic. So where we'd like to move from state 1 up to state 2s, rather we move from state 1 to state 2a with a slightly higher entropy. Now it turns out that the exiting pressure is set. You set the exiting pressure based on what's needed, right? If the pressure at the exit's not large enough, you have to have a bigger pump. So the pressure change is set no matter what you do, whether you had an isentropic pump or a non-isentropic pump. And so the exiting pressure will be the same in both state 2A and 2S. But what's different is that state 2A actually has more enthalpy in it because some of that friction, some of the non-idealities in the pump cause the pump to require more work to get the job done, right? To get the exiting pressure up to where we want it to be. And so the enthalpy change across each of the processes from entrance to exit in the real case and the ideal or the isentropic case, they are different, but they are each proportional to the amount of work required in order to raise the pressure of whatever fluid is flowing through the pump. And so we can talk about the isentropic pump work as the work that we should have to put into the pump over the actual work that we have to put in, because the actual work we have to put in will be greater than the amount of work we should have to put in, because some of the energy goes into thermal energy in the exiting stream rather than just into flow energy. Now, we can actually calculate the isentropic work very easily. If we're talking about a pump, we're talking about a fluid that's probably pretty incompressible, and so V delta P is the easy way to calculate the isentropic pump work, the amount of work we should have to put into the pump. But the actual enthalpy change is the only way to calculate the specific work. And again, there's a tilde in this equation because we're neglecting kinetic and potential energy changes in the fluid. So this is a good equation and good thing to understand about pumps, because each pump will have its own isentropic efficiency. The one with a higher isentropic efficiency is going to require less work in order to pump the fluid up to the higher pressure that you require, and what will happen is the exiting temperature will be lower, right? Because less of the energy that you've put in via work will be transformed into thermal energy in the exiting stream. Compressors also have an isentropic efficiency. We'll start off with a TS diagram, recognizing, as we did with the turbine and the pump, that there's going to be a difference between the actual performance and the ideal performance. So in a compressor, the exiting gases are going to have a higher temperature than we would like for them to have because of inefficiencies, non-idealities, and irreversibilities essentially. And again, we can play the same game where we're thinking about enthalpy instead of entropy, because it's the enthalpy change that's proportional to the work rather than the temperature change. So the isentropic efficiency of a compressor is the isentropic work, what we should have to put in, over the actual compressor work. And here we'll have a ratio of enthalpy differences rather than having a nice equation like we did for a pump. So this looks a lot like what we had for turbines, but it's the other way around, because, you know, if you're thinking about a turbine, the amount of work you get out is not as much as you should get out, right? You're being gypped both ways, because the amount of work you have to put into a compressor is more than what you should have to. It's kind of like buying and selling, right? You never sell something for as much as you think you'd like to get out of it. You never buy something as low a price as you would like. Well, sometimes you might, but most of the time that's not the case. So they're like mirror images of each other. Now, since compressors are not typically operated isentropically, and so we don't really want to compare it to isentropic behavior. Rather, we can do better by cooling the gas as it moves through. Since that's the case, what we'd like to do is actually use a compressor efficiency that's the isothermal compressor work over the actual compressor work. So that's a little more common, a little more, well, a lot more common, and a lot more useful definition of compressor efficiency. Rather than thinking about isentropic efficiency, rather we'd like to compare it to isothermal case. So that's the way these are usually compared, because most compressors are actually cooled as they compress gases. We can talk about nozzles' isentropic efficiency as well. Again, a nozzle will not behave ideally, right? The entropy of the gas flowing through it will increase, and you can see from the diagram, the TS diagram, what that does. You end up with a temperature at the exit of the nozzle higher than it should be. The nozzle doesn't use the flow, it doesn't convert the thermal energy into flow energy as well as it should. And so, again, we'll go back to considering the enthalpy change. The only thing is that really the purpose of a nozzle is to generate kinetic energy at the exit. So we're going to talk about the ratio of the kinetic energy actual versus kinetic energy at the isentropic nozzle exit. And so instead of just dealing with enthalpies, we are certainly interested in the kinetic energy changes. And so kinetic energy is just, you know, mv squared over 2, right? And so that's why we've We don't have the 2 here, they cancel out, but we do have the velocities squared. So this is the way that we will define a nozzle's isentropic efficiency. Now we can calculate that again by the ratio of the enthalpy changes, because remember what a nozzle does is it converts enthalpy into kinetic energy. And so both these equations talk about nozzle isentropic efficiency. And basically you can set the velocity, the square of the velocity ratio, equal to the enthalpy difference ratio there that you see. There's another section in the chapter, it's 713, but is not part of this course. I wanted to make sure you knew that so that you don't have to worry about it. So you can smile and be glad that that's not, this chapter has enough in it without that.